All right, so section 5.2 is the indefinite integral. And so in the last section, we talked about antiderivatives, and we needed a point on a curve, and we could figure out the area under the curve. Specifically in this section, we're going to be talking about antiderivatives and how we come about finding them. Okay, a couple of important definitions in your book. This constant of integration is huge. Okay, when we have an indefinite integral, that means we're not setting any bounds. Okay, so no interval. So in order to have the correct antiderivative, we need to make sure we have that plus c, that constant of integration. Okay, so integral notation. When you take the derivative of an anti, you're going to get the original function. So the derivative of an anti is going to give you the original function. Okay. Notice for notation, we use a capital F for the anti. That'll change later in the book a little bit, but for all intents and purposes, this is common practice. Capital F represents an antiderivative. And again, notice we have no bounds, and therefore we have to have the plus c. Okay? So a derivative and an antiderivative, these two operations will undo each other. And so when you take the derivative of an integral, you're actually going to get whatever was inside the integral. Okay? All right, examples for integration. We did a couple of these yesterday. Here we go, x cubed. If we take the derivative, we're going to get 3x squared. If we take the antiderivative of 3x squared, we should get back to the original function. Because we have an indefinite integral, we're going to include the integration constant, or the constant of integration. Remember when we do exponents, the exponent comes down in front and you subtract 1. It's going to work exactly the opposite for an anti. We're going to put that number back up, add 1. Okay, so this is going to be important. You do not have to memorize these are just examples. Okay, this table, I hate the tables. Don't memorize any of these. You'll figure it out, okay? If you know your derivatives, then you can just think backwards. You're just thinking backwards. Okay, you do not need to memorize this table. Okay, so let's do some examples. If we have x to a power other than -1, we're going to add 1 to the exponent and divide. So, for example, we had x squared. Take the exponent and add 1. So we get x cubed. Okay, since 3 is our new exponent, we would multiply by the reciprocal of that, and then plus c. So here, the exponent is 3. You're going to add 1, and then you're going to divide by that same number, or multiply by the reciprocal. Okay, and this is going to be valid for any number other than -1. Any number other than -1. Okay, so general properties. Keep this in mind. These are the same things that we talked about in Algebra 2, no, it would have been pre-calc. We talked about these in pre-calc when we do summation notation. They're also true here. We use these same rules for when we took the derivatives. Okay? So if I have a constant, I can pull it out front. Okay? If I'm adding, I can separate them and do them as individual integrals. If I'm subtracting, I can separate them and do them as individual integrals. These become your properties for integrals. Again, the anti, and the integration constant. Okay? Notice this c. An example of this would have been 3x squared. The 3 stays, you take the derivative of that, and you get this. Okay? So we use the idea of the constant before. We're going to use that same principle now. Okay? So this idea stems from the same rules that we had before. Okay? Okay, so let's do some examples. The first two, I'm going to write every step out. We're going to pull the constant outside of the integral. Okay, pull the constant outside the integral. And this is going to become 4 times, and now it can be whatever. So I have to think, what is the derivative here? Well, I'm looking for whatever function has a derivative of cosine x. And because c is undefined at this point, I can either put the c in or put it out. It doesn't matter, but my final answer is 4 sine x plus c. Now, the same way we did derivatives before, this right here is going to be split up into two integrals. And each integral needs a dx. And so I have to think this is the one that has an exponent of 1. So add 1 to the exponent. Now divide by the new exponent. Plus add 1 to the exponent. Now divide by the new exponent. I tap on the constant of integration. Okay, so the parentheses here is telling us we're taking the derivative of both pieces with respect to x. Important that this is the same as this variable. That's going to become a very big issue in chapter 6. So keep in mind that that has to stay constant. Okay, so this example's actually worked for you. Notice that what was done here is the constants here were pulled out every time. So the 3 is pulled out, the 2, the 7, and there you go. So now when you do your anti, you add 1 to the exponent, divide by that number. Add 1 to the exponent, divide by that number. Add 1 to that exponent, divide by that number. Okay, this right here is really x to the 0, correct? So add 1 to this exponent, you get x to the 1 divided by 1, you don't write it. And in order to be completely finished, we have to have the plus c. If you do not put the plus c, you are just wrong. Okay? All right, and now we want to evaluate. Well, this is a little bit harder because you have to do some thinking. At this point right now, you don't want to work backwards on the quotient rule. So what we want to do is use some of our identities from pre-calc or earlier in calc and find a way to simplify this. So I'm going to go ahead and say that this is really and just so that we're clear, here's what I said before that. To my head. So 1 over sine x is cosecant x. Now cosine x over sine x is actually cotangent x. So what I'm really taking the derivative of is cosecant x, cotan x, or cotan x, cosecant x. Here's the good news. This is one of our identities, our primary derivatives from the trig section in chapter 2. And that is actually the derivative of that. I'm going to grab a book just in case you haven't memorized your trig derivatives. In your book, they're actually on the front cover. You will have some integrals for those, so you can see those on the very front cover. And then your trig derivative, I'm trying to find the exact page. I think it's section 2.5, but it should be 2.6. It's 2.5. So in section 2.5, it's on page 170. That's going to be the ones that you will have a harder time with. Okay. So now let's do example B. So again, I don't want to use the quotient rule. So I want to break this up into two separate fractions. And again, all of this is getting to t. So this is really t squared over t to the 4th dt minus the integral of 2t to the 4th t to the 4th dt. And so this is going to reduce to 1 over t squared. This is going to reduce to just 2. Now all I did was rewrite that fraction. So when I do this, this is really, again, I'm writing out every step on day 1. Eventually you won't have to. You'll be able to do a lot of this in your head. So now add 1 to this number. Divide by the new exponent. Minus, add 1, tack on your integration constant. Now, do I have to write it like that? No, I could write it like this. And that would work just as well. Okay? All right, so I'm going to group this, and I'm going to, I want to group, oh no, Miss Collins, I want to group all of this. Oh, okay, so I want to group all of this. I just need to shrink this down so I have room for the other one. Okay. So now let's do this one. And here I'm going to run into a problem because I cannot separate that denominator. So I have to find a way to make that work. And so this one's actually hard. I'm surprised Mr. Clinton put this one in here. I'm going to do something. If you're confused on this one, just put a little phone call video. So what I'm going to do, I'm actually going to put a +1 on top, but I'm also going to put a -1 on top. And the reason I want to do that, and I'm going to put all of this dx. And the reason I want to do that is because it's right here. I want to make this be the integral of x squared plus 1 over x squared plus 1 minus 1 over x squared plus 1. I know. This is one of those round the beaten path ones where it's going to look uglier before it looks better. So this is just the integral of 1 dx minus the integral of 1 over x squared plus 1 dx. Now this right here should remember as a derivative of tangent or inverse tangent. It's from that same derivative section. Now I want to say inverse derivatives for 2.6. So I'm going to get x, that's the derivative here, anti. So the anti there, and then this is going to be minus. Now when I took the derivative of inverse tangent, I got 1 over x squared plus 1. So this must be inverse tangent x plus. Now I'm going to pull Mr. Clinton on board method here. I think I'm right. Someone double check that. Look in your book. That should be the derivative to the inverse tangent. I'm going to go with it because I feel good about it, but I could be wrong. Bonus points if I'm wrong. Okay, so let's do the last question. It says, sir, suppose that a curve y equals f of x in the xy plane has the property that each point, so it's telling me this is this, which also tells me that the derivative of f is equal to x squared. If I know that's the derivative, I should be able to anti that. I should be able to anti that. I should be able to anti the derivative and get my original function. So if I anti this, I'm going to get x cubed over 3 plus c. I'm saying that this is the anti, right? And if that's true, that should give me my original function. However, the plus c needs to be fixed. So we need to plug in those 2 points, because what I'm really saying, and that should work for all points. And since I have this point 2, 1, it should work. So 1 equals 2 cubed over 3 plus c. And then 1 equals 8/3 plus c. So that means c must equal negative 5/3. 3/3 minus 8/3 is negative 5/3. Oh, Miss Collins, you're wrong. Sorry. There's the 8. So now y equals x cubed over 3 minus 5/3. So if I'm given a point, then I can solve for the integration constant. If I don't have a point, if I don't have a specific place, I'm going to go ahead and leave it as plus c. Okay? That integration constant has to stay. Okay. We talked about differentials a little bit earlier in the unit, but not a ton in the semester. So there's a couple of things that you need to know. This right here is a general terms. And it's basically saying if you have the derivative of y with respect to x, that's your original function. That's really all it's saying. And if that's true, some function, it does not matter what this is, it could be anything. But in order to use our integration rules, remember that your integration has to be the derivative taken at a specific variable. So in this case, we're taking the derivative of y with respect to x, which means f here, this has to be in terms of x, which means I need all my x things on one side and all my y things on the other. So again, I'm an idiot, so I'm going to keep it simple, stupid. These initial value columns are a huge portion of the AP exam, by the way. They're used very, very often. So what you want to do is you want to move all the x's to the other side. So back in Algebra 1, if you had a fraction with a denominator, you undid the denominator by multiplying both sides by dx. So if I multiply this side by dx, it goes away, and on the other side I'm going to get dy equals cosine x dx. Notice that the y's and the x's are on opposite sides. Now I'm going to take the antiderivative of both sides. What that means is, on this side I'm just going to get y. On this side, I'm going to get what I was getting earlier, the derivative. Remember, this is the derivative of something plus my constant of integration. But now I'm being told that I have a point. This is the x, this is the y. So I'm going to plug them in. 1 equals the sine of 0 plus c. That's going to give me the initial value. So in this case, I get 1 equals the sine of 0. So c has to be equal to 1. So now the original equation that gave me this differential equation must have been sine x plus 1. So a differential equation is simply asking you to use a differential, i.e. a derivative slash integral, and solve for the c. So it's just another way of phrasing the same question. The only difference is before we were using f of x, and now we're using this y, dy. Okay? Let's do another example. Slope fields. Woohoo! Not really. Do you see this right here? We would rearrange it. We would anti both sides. And so really what that says is your parent function must have been a cubic over 3. And so what you see here is the family of curves, that would be valid. So this could be x cubed over 3 plus 1, x cubed over 3 plus 2, x cubed over 3 plus 0, x cubed over 3 minus 1, x cubed over 3 minus 2. It's just a family of curves that have that slope. And so you can kind of see if you take these lines and you go like this, you can see, look, they're horizontal here. I'm just kind of drawing to see how I'm making my dashed lines. If you connected them, those would be the curves. Okay, so slope field, and we only talk a little bit about this. We'll come back to it again later in the chapter. But it's just a very small piece of the actual portion of differentials and antiderivatives, okay? There's typically a question, and it's super easy to do. Okay, here's your quick check. It's on page 329. You're going to go to page 332 for the answers. Yes, Ms. Collins expects you to come to class on Tuesday with this done. Yes, I'm going to be checking notes. And honestly, I hate the sound of my own voice, so I do not want to watch this video in class on Tuesday. Really? Do not want to watch this video in class on Tuesday. So please watch the video, take notes, and come to class with questions. I'll give you the bookwork assignment when you come in on Tuesday so we can go over this. Good luck.